In this video, I talk about correcting non-constant variance by taking the log of the y variable. I suggest using the log transform because then your result is going to be interpretable. I'm going to go over how to do it and how to understand it and how to describe the regression coefficients in this setting. And then at the end, I show you how to do the math part for it, in case you're interested in how we got there. So the example I've got for this problem is about needle area of a tree. So to find out the needle area of a tree, usually they have to destroy the tree. So instead, we're going to try to make a predictive model for a needle area using the height and the caliper, which is the diameter of the tree trunk, measured at 4.5 feet. So I've just fit an ordinary linear model here with caliper and height and needle area as my outcome. You can see that when I plot the residuals against the fitted values, there's non-constant variance. So at the beginning, the variance around those points looks pretty small, and then it starts to get bigger, and it gets real big towards the end. It kind of looks like it shrinks back down, but then it's really hard to tell because by the point you're out there, there's only like a few points, so it's harder to tell what's going on towards the right-hand side of the plot. It also kind of looks like a U shape, like that. This makes it a pretty good candidate for this log transform. So to actually transform the y variable, I just took the log of the needle area in my data frame and made a new variable that I called ln for natural log needle area. In R, log is log base e, so it's the natural log. I then fit a new model using that log needle area. You can see now the residual plot looks much better. There's like very little going on here. It looks pretty much constant. Everything looks okay. So we're going to go with this model, and I'm going to show you how you would interpret the coefficients. So here's the output from this model. The estimates right here are in the summary output, like the 1.62 and the 0.069. Those guys are for the log needle area. It's a lot better if we can try to interpret it just in terms of regular needle area. So what we do is we exponentiate it, and because of that log transform, this is on a multiplicative scale. So down here I've exponentiated the coefficients, and the one for caliper, you can see, is 1.0717. Now, that's a multiplicative increase. I'm going to write it in terms of a percent because I think it sounds better to call it 7.2% increase rather than a 1.07 times blah, blah, blah. So over here, I'm saying I'm going to fix the height. So we got to keep height constant, right? And then we can talk about when we increase caliper, it's a multiplicative change in needle area. So for trees of the same height with a 1 foot difference in caliper, those with the larger caliper are estimated to have a median needle areas that are 7.2% larger. If you don't have something that is in like 1 point something times bigger, so in this point, caliper and height, the effects here are between 1 and 2. So if we go over 2 or we go 2, it sounds weird to say like a 200% increase or like a 327% increase. So if it was like that, I might instead talk about that the one group had a median which was 2.46 times larger. Likewise, if it's less than 1, it sounds kind of weird to say like you'd get like a negative I don't know how to explain that one. It's like it's 0.24, yeah, of the bigger one. I don't know. So instead, I convert it into something where I can say it's some percent smaller, right? So 24 times one group would be the other group. So that would be 76% smaller. Finally, the math bit. So this would be the model that we fit. You can see that we took the log of the y's. You can't take the log through the expected value. That's not allowed, right? What we can do, though, is we can start talking about the median, and we can say, okay, this expected value is pretty much equivalent to the median. And we can only say that if our residuals have about the same number of points on top as it does on the bottom, all across there. So if your residual plot looks about like this, and you have symmetry about that 0, then your median is going to be the same as your mean. So now I'm going to start talking about the median log of y. With the median, I can take the natural log through. So here's my natural log, it's come through. And now to get rid of the natural log, I'm going to do exponentiate everything. Now I'm going to go ahead and compare. So I'm going to look at beta 1, and I'm going to compare a group where x is 1 larger for x1 is 1 larger and x1 is 1 smaller. I'm going to divide them. And when you divide things that are exponents, they subtract. So the beta naughts are going to go away. The beta 2 x2s are going to go away. The beta 1 x1s are going to go away. And I'm just going to be left with a beta 1 because, distributing. So that's where that's coming from. So now you can see that it's a multiplicative increase between the bottom times this e to the beta 1 to get to the top.